last week. Anything that you want to go over? Hi, Kira.
Hi.
How you doing?
Hanging in there.
You hanging in there? It's going there. It's getting there. Just 5 weeks. You're getting there. So, so today I want to go through a couple of more problems involving torque and looking at different configurations of torque on using different points of rotation. We're gonna do a couple of problems very similar to the one on Friday. Then we're gonna do one problem that involves using the moment of arm, and hopefully you will see how you apply the moment of arm. Is actually quite useful for calculating torques in the human body. Wednesday, we'll continue to do some problems, and then we'll do some review for if you have any questions for your exams or anything you want to do, we can do some review. The homework due on Wednesday, most of it is only torque problem. So you will see that, I mean, they will be in your exam on Friday. I'm spending a lot of time in torque, especially because for those of you that are going for physical therapy or that you think that you're going to be working in some kind of rehabilitation, this is something that's you're gonna see it again. And when you go to grad school, this is a topic that it definitely you're gonna see it again. So I'll spend some more time on this. But if you have any question, if you have, you want me to go through any topic, you want me to go back, you want me to do the questions a little more detailed, please let me know, and I'll do it. Okay. So let me try to set. Yes.
For the exam on Friday, are we still having like class at our normal time?
I'll be here. Well, I'll be in my office, but I'll be no. So first of all, no, we don't have sessions. We don't have a lecture. I'm not gonna cover new material, but I will be available in case anyone wants to start their exam or they want to go through more problems, if they have questions or whatever, I'll be available. So no, there will be no class, but I'll be here. Okay. But yeah, good question. I keep forgetting I'm saying that. Oh yeah. Okay, so we're gonna start with a problem with the bicep, and we're gonna try to. Kelly's asking, will the due date for the exam will be on Friday or by the end of the day? So the way the exam is gonna work, you're gonna have a 48-hour window. So you can start your exam anywhere on those 48 hours. So I will open the exam on Friday, and I will close it Saturday at almost midnight. So you can start taking the exam anywhere in that window. Once you start the exam, you're gonna have probably like 2 hours, 2.5 to complete the exam, and then you can do it when you feel when it's more convenient for your schedule. I don't want to do it during the time of the class, because if you have a class after this and I give you 2 hours to finish the exam, you're not going to have those 2 hours. You're going to have to stop earlier. And also, I know that some people are going to travel back, are going to go home or whatever. So I'd rather for you guys to organize your time, and I'll give you that window. Does that make sense, Kaylee and Kennedy? Okay. Well, I think yes. Okay. Can you guys see in the chat? Can you see the drawing of the bicep? So okay. So this is a very simple schematic of the bicep. We're gonna have a couple of assumptions. I'm gonna assume that the length of the arm here is gonna be 30 centimeters. I'm going to assume that the mass of the arm is 3 kilograms. And I'm going to assume that this barbell has a mass of 5 kilograms. Okay. What I want to find out are two things. I want to find out what is the force of the muscle, what is the force on the bicep. So I want to know what is this force. And I also want to know what are called the reaction forces. So every time you have a joint and you're going to have forces in different directions, you're going to have a reaction force. And so I want to know what is this. And I'm going to call this FR, just for reaction force. Okay, we talk about that. We did an example like this before with the deltoid when we calculate the force on the shoulder. We also calculated the reaction force. We didn't call it like that. We just call it the force at the joint. But the technical name is the reaction force. Okay, and the other piece of information that I need is that this force of the muscle is not perpendicular to the arm, is tilted a little bit backwards. So I'm going to say that this angle over here is going to be 15 degrees. Okay. Does the drawing make sense? So what I want to do now is I'm going to let you guys do everything from the beginning. So this is a problem. I want to find out what is the force of the muscle. I want to know what is the reaction force. Let's start, everybody, with calculating the force of the muscle and give it a try. You may get stuck, that's fine. I just want you to try. This is a very classic, this is a problem from an exam. So I want you to get idea of what it takes to solve, how to set up the problem, what are the questions you need, and how to start thinking about these kind of problems. And for the people in the chat, when you're working with it, you can take a picture and send it on the chat, or you can open your camera and then just show it in front of the camera, and then I can take a look. Oh, there's one more information. So the insertion point of the bicep is going to be 2.5 centimeters from the joint. So this is going to be 2.5 centimeters.
So that would be the first thing. This angle to the something. You can draw it, but if you're putting your origin here, there will be no job, you will come on job. So just for the job to.
You show
No, you don't know where it is. You don't know if it's going to be in the X or Y direction, so you just put it in a random direction, and then you should put it like from the top to the up and to the, yeah, sorry, up to that to the right. So be careful because this force is not at the jump. It's 2.5 centimeters in front of the jump. Yeah, so a couple of things. The angle is also to the other direction. Yeah, and it's 2.5 centimeters in front of the jump. So the direction is fine, but these forces are at the jump. Is 2.5 centimeters in front of the jump. Okay.
Okay.
Alexis, show me your work. Oh crap. Looks good. Perfect. Thanks. I didn't hear you, but looks okay. And who else? Who else should I ask? Erin, how you doing, Erin? Can you show me your work? Oh, I don't see anything. This is not gonna work. Okay. Okay, so a couple of things with the, I'm gonna do the free body diagram. And for this free body diagram, I'm gonna place, well, I'm gonna do the free body diagram and I'm gonna look at all the forces that I have. So I'm gonna have the force of the dumbbell, of the barbell here. I'm gonna have the weight of the arm. I'm gonna have the reaction forces here, and I'm gonna have the force of the muscle somewhere around here. So this is the force of the muscle, and this is gonna be the 15 degrees. Okay, so again, when you are working with these kind of problems and you have a couple of knowns, try to place your frame of reference, the origin of your frame of reference, put it somewhere where you have an unknown force. So in this case, we have two unknown forces. We have the reaction force and we have the muscle. So I'm going to try to solve for the muscle. So I'm going to put the frame of reference here at the reaction force. And I think this is what most of you did. Okay, so this is going to be my frame of reference. And then from this frame of reference, I can set up all the distances that I have. So this is going to be 2.5 centimeters. This is going to be 15 centimeters. And this last one is going to be 30 centimeters. And I think those are going to be all the distances that I have.
Did you get the 15 just from thinking half 30?
Yeah, so if you don't have any information, you can assume that the arm is kind of like a rectangle, and you can put this center of gravity right there in the middle. There are some problems that told you where the center of gravity is. Okay, so these are the forces that you have. This is going to be the frame of reference, and with these kind of problems, we only have 3 equations. There's no more. Even though it feels like we have seen like a bunch of equations, we have only seen 3 equations. All the forces in X are going to be equal to 0. All the forces in Y are equal to 0. And all the torques have to be equal to 0. Okay? I'm going to be working with the torque right now. Okay? And I'm going to work with the torque because by working with the torque and choosing this frame of reference, I can eliminate this force. Well, I can ignore the effects of the torque of this force. So it simplifies the equation a little bit. Something that I cannot do if I work with the sum of forces in X and the sum of forces in Y. I cannot eliminate any force. So I'm going to do it with the torque. And basically, the sum of torques is going to be the torque of the muscle times the torque of the arm plus the torque of the barbell. We also technically have the torque of the reaction force, but we know that that one's going to be 0 anyway, so we can ignore it. Now, the force of the arm, the perpendicular component, the one that I need is going to be this component over here. That's the perpendicular component. And that one is going to rotate the arm counterclockwise. So that one's going to give me a positive torque. The other 2 forces, caused by the weight of the dumbbell and the weight of the arm, they're going to rotate the arm clockwise. So these 2 are going to have a negative torque. And also the angle between these forces and the arm is going to be, it's already 90 degrees. So that's something that we'll need to consider later. So I'm going to write down the equation for the torque. And this will be, the torque is the distance to the force from the pivot point times the perpendicular force. So I will have, for the muscle one, I'm going to have 0.025 meters. Oops. I don't think anyone is seeing. In the chat, can you see the paper?
Yep.
Was that a yes or no?
Yes. Yes.
Oh, you can see it? Oh, cool. You have the distance to the force. So this is the inch that you have from your joint to the insertion point. And we need the perpendicular component of the force. So that's going to be the magnitude of the force, Fn, that I want to find out. And then the perpendicular component is going to be cosine of 15. You can use cosine of 15, or you can use sine of 75. Either one will work. Okay? But that will give you, these will be the perpendicular component of that force. Now, the other 2 forces, the other 2 torques are relatively easier. So we're going to have the distance, 115 meters, times the force, the force of the arm, and that's going to be the weight, which we said that it was going to be 3 kilograms times 9.8. We have a sine of phi here, but it's sine of 90 degrees, so that's going to be 1. So we don't need to write it. So this is going to be 1. And then for the dumbbell, we're going to have 0.3 times 5 times 9.8. And this is going to be equal to 0. Yeah? Makes sense? From here, I can solve for this force. So I'm going to do it in a couple of steps. So I'm going to, all the terms that doesn't have that force of the muscle, I'm going to put it on the right, and everything else I'm going to keep it on the left. So here I'll have cosine of 15, and on the other side, we're going to have 115 times 3 times 9.8 plus 0.3 times 5 and 9.8. And then to solve for the force, I'm just going to divide the left side, the right side, I'm going to divide it, for everything, I'm going to divide by 0.025 times cosine of 15. Okay. Okay, and I have 791.4 newtons. Yep. Is that what everybody got, or something like that? Something close to that number? Okay, again, you can see that the force on the bicep is almost 10 times bigger than the total weight that you have. Like if you look at the mass of your arm, the 3 kilograms, and the mass of the dumbbell, that's 8 kilograms, that's 5 kilograms. So together, there's a mass of 8 kilograms. You multiply that by 9.8, you're gonna get something around 80 newtons, a little bit less than that. However, the force of the arm is almost 10 times that. Now, if you look at the distance between the joint and the dumbbell is 30 centimeters, and the distance between the joint and the dumbbell and the muscle is 2.5 centimeters. So this one is almost 10 times bigger than this one. So it makes sense that the force that the muscle is going to require is going to be close to 10 times whatever you have on your hand. You can think of it as a seesaw or a scale. So if you have a seesaw and you want this to be completely balanced, well, you will have your two kids to be the same weight. So if you assume that this distance is the same as this distance, you will need the two masses to be exactly the same, so the seesaw is in balance. But if you have something that looks like this, and this distance is 5 times this distance over here, then you will need this kid to be 5 times as big as this one to keep things in balance. This guy is going to create a torque that's going to be 5 times larger than whatever you have here. Okay, so by looking at the location of where your load is going to be and where your muscles is inserted, you can get an idea of how big those muscles are gonna be, okay? Oh, sorry, how big the force of the muscles is gonna be, okay? Makes sense? Ish? Okay, so we calculated the force on the muscle, and we need to calculate now the reaction force. We already used this equation of the torque. So to calculate the reaction force, we need to use the other two. Okay? So when you're working with these equations, you can work with the traditional free body diagram that we usually work with. So I'm going to have the weight of the arm, and I'm also going to have the weight of the barbell. I'm going to have the muscle pulling up. And again, this is going to be 15 degrees. And the last one that I need is going to be the reaction force. And again, I don't know anything about this reaction force. I don't know where it's going to be. So I'm going to assume that it's just going to be somewhere around here. Somewhere that I make the two components of the force to be positive. Okay, so I know that the force of the muscle, what is 791.4 newtons at 15 degrees. The force of the arm, that's going to be 3 times 9.8, and the force of the barbell is going to be 5 times 9.8. Okay, so those are the forces. The equations that I need to solve are the sum of forces in x equals to 0, and the sum of forces in y equals to 0. I'm going to start with the x direction. Now, in the x direction, I only have two forces. I have the x component of the reaction force, and I have the x component of the muscle. The two weights are along the y-axis, so they don't have any y component. So I'm going to have the x component of the muscle plus the x component of the reaction force. That's going to be equal to 0. The x component of the mass, sorry, of the muscle, that's going to be negative Fm sine of 15. Again, it can be sine of 15, or you can use cosine of 75, whatever angle you prefer to work with. Yep. And the x component of the reaction force, I have no idea. So I just solve for that one. This will be 791.4, sine of 15. And I got 304.8 newtons. So that's the value of the x component of that force. Okay?
I have a question.
Sure.
How come we use the sine of 15 here and then above it we use the cosine of 15 to the other one, even though the angle is drawn the same?
Well, in this one, I calculated the x component.
Okay.
And in the previous case here, I'm calculating the one that's perpendicular. So you can imagine this along the y-axis. So that's why in one case you calculate with the cosine, and in another case you use with the sine.
Okay.
It just depends on what component are you looking for. Okay, so now try to calculate the y component on your own.
So calculate magnitude and direction. Yeah, so you use all the decimals on the details of, I'm carrying an error with calculators. So, yeah, you'll be okay. Just be careful with your stuff. Because here you have negative loss with x component equals 0. And then so over here, yeah, be careful with the stuff. Because this one is going to be positive. Is that the what component? Yeah. Yeah, so when you solve, it's going to be negative and this is going to be positive. That's what we saw. That's what our hypothesis was that it was to go up. But when you solve it, you can see that it is not. It's actually going to go somewhere around here. And we can try to calculate the angle. For the y, no, positive x, negative y. So you can see that this force is almost opposite to this. Okay, so if I try to calculate the y component, I'm gonna have 4 forces in the y direction. So I'm gonna have the y component of the muscle force, I'm gonna have the y component of the reaction force, and I'm gonna have the weight of A and the weight of B, and those are gonna be equals to 0, okay? This is what I want to find out. I want to find out what is that y component of the reaction force. So for the y component of the muscle, I'm gonna have 791.4 cosine of 15. It's gonna be positive. I'm assuming that that reaction force, the y component of the reaction force is gonna be positive too, so I'm gonna do it like that. And then the two weights are gonna be negative. So I'm gonna have minus 3 times 9.8 minus 5 times 9.8, and this is going to be equal to 0. Solving for the y component, I'm going to have negative 791.4 cosine of 15 plus 3 times 9.8 plus 5 times 9.8. And Mary, what you got?
Negative 686.
600.
And 86.03 newtons.
03 newtons. Okay. Once you have the y component and the x component, we can calculate the magnitude. And Sylvia, what you got?
I didn't get that far.
Emma, what you got?
I didn't even.
Oh. Anyone in the chat? Any one of you got to that magnitude? So I got a magnitude of 715.9 newtons, and the angle is going to be 73,
Yeah.
close to 73 degrees. Okay?
How did it be?
And the way you calculate the angle is the arctangent of the y component over the x component. Lisa, for the magnitude, the way you calculate the magnitude will be 686 squared plus 204.8 squared and all this. So check your math. The 73 will be below the x-axis. So you're gonna have something like this. So if you see that reaction force and you compare it against the force of the muscle, they're almost collinear. They're almost like 180 degrees out. If we didn't have, we didn't consider the weight of the arm, they will be perfectly 180 degrees from each other. They will pretty much match, and they will cancel each other. Make sense? Okay. Now, in the case of, yes, Mary.
So is it, in these problems, is it always gonna be like that? Like they're basically opposite of each other?
Close enough. It's gonna depend on how many forces that you're gonna have. Like in this case, we only have two load forces. Like in this case, is the weight of the arm and the dumbbell, and then you have your muscle. So because you have very few forces and the values are very similar, they're almost going to be 180 degrees, and they're almost kind of opposite to each other. If you had more forces, or the difference between the forces will be bigger, then you're going to be moving away from those 180 degrees. Yeah? Okay, I'm going to show the math for the angle. If I can find a piece of paper, there you go. Okay, so for the, I'm going to repeat the angle. So for the angle, we have two components. The x component that we said was 204.8 newtons, and we have the y component, which is negative 686 newtons. So if we draw this vector, it's going to be something like this. And we want to find out this angle over here. So I'm going to draw a triangle rectangle that's going to look like this. And remember, tangent of theta is opposite over adjacent. So the opposite of this angle is the y component, and the adjacent of this angle is the x component. So tangent of theta is the y component over the x component. And then to calculate theta will be the inverse of the tangent, or the arctangent, of the y component minus the x component. So in this case, negative 686 over 204.8. And that will give you the 23. Does that make sense, Grace and Alexis? Okay. Yeah, everybody's clear also how we calculate that angle? Oops. Okay, so a couple of things. If you look at the anatomy of the shoulder, if you look at the anatomy of the arm and of the knee, so you will have a pivot point. You will have a muscle that's going to be either pulling up or pulling down, depending on if it's the quads or is the, what's the names of the pullback? Or the hamstring, depending when you are, if you are pulling or pushing your triceps or your biceps, but you're going to have something like this, and then you're going to have your loads on one half. So you have some loads, then you have a muscle over here, and you're going to have a very small insertion point, and then you have a very large loading arm. Okay, and this is very common for any part of your anatomy that has a big range of motion. You're gonna have this configuration. Pivot point, the muscle, and then the loads are gonna be farther away. Again, you're gonna have a really big load on your muscle compared to the values of the object that you actually pushing or trying to move. And you do that in order so you can have a big range of motion. So this is a very common configuration. Again, this is very common for your arm, your shoulder, your knees. This is a very common configuration. Now, if you look at something like the foot, the foot has a different configuration. So instead of drawing the foot like this, I'm just going to do a foot that's going to look like a little bar. Now, the pivot point is going to be somewhere around here. The Achilles muscle, the Achilles tendon is going to be on the back. And then you have the weight or the normal force somewhere in the toes. So this is going to be a normal force. And this is going to be the Achilles tendon. So now the configuration is a little bit different. You have the muscle, the pivot. Now you have the pivot point in between the two forces that are opposing. So it's a little bit different. And that affects the forces that you can support, and it affects a little bit the range of motion that you have. So now the range of motion of the toe or of the ankle is way smaller than the rate of motion that we have in our extremities, the ones that we have in our feet, or that we have in our leg or we have in our arm. But the tendon, this Achilles tendon, can carry a lot of weight. So you reduce the range of motion, but now this one is going to carry way a much heavier load. So we're going to try to solve this problem. We're going to assume that we have a person and the mass of the person is 65 kilograms. So that would be, I think, something around 160 pounds or 170 pounds. And he's doing tiptoe just on one foot. And we want to find out what is the force on the Achilles tendon. Okay? Now, many people think, okay, if I'm supporting on my toes, then it makes sense that the toe is going to be my pivot point. But if you do that, the only force that you know is your weight, and you know that you're going to have a normal force here. So if you put your pivot point on your toes, you're going to get rid of the torque created by the normal force. And then you're not going to have this force. And there's also, in every joint, you're going to have a reaction force. So you're going to have a reaction force that you don't know which way that one is going to be. So you should not put your pivot point in the normal force. You should not put it on your toes, even though it kind of makes sense. A better place is to put it sorry, a better place is to put it on your ankle, on that joint. Yeah. Now, measuring the angle, like in real life, if you have a patient and you ask the patient to do a tiptoe, measuring that angle is hard. Because the person is going to be moving, and if you have extra load or if the person's carry something, it's going to be moving. It's really hard to keep that position. But you can ask the patient to remove the shoes, and you can actually measure the distance between the ankle and the heel, and you can actually measure the distance between the ankle and the toe. And you can actually measure the distance of the toe. So you can get these distances. So on this particular position, the distance between the Achilles tendon and the ankle, we know that this is going to be 4 centimeters. And the distance between the toes and the ankle, this again is going to be 12 centimeters. Okay, now this configuration with the pivot point in the center, that's the one that we were talking about just a minute ago. That's your seesaw configuration. The pivot point is right there in between the two loads, or the two forces. So this force on the Achilles tendon, because it has an arm that is 3 times smaller than this force has to be close to 3 times larger. So we just need to make sure that that appears on the equations. But whatever weight you have, the Achilles tendon is going to be 3 times larger. We just need to make sure that that shows in the equation. Now, the way we calculate torque, the way that we will be using to calculate torque, is the distance times the perpendicular force. But to calculate this perpendicular force, you need this angle over here. And if you don't have that angle, then there's no way you can calculate that perpendicular force. There's another equation that we talk about, and it's basically where you can also say that the torque is going to be the amount of the force times the moment of arm. And the moment of arm is the shortest distance between the force and the pivot point. These numbers over here, that's the moment arm. And it's very easy to calculate or to measure in real life. Again, if you know the distance between the heel and the ankle, if you know the distance between the toe and the ankle, you can calculate that that moment of arm. So this 4 centimeters is going to be the moment arm for the torque of the ankle. This 12 centimeters is going to be the moment of arm for the normal force. Okay, so we're going to calculate the torque on the Achilles tendon. So the sum of the torques has to be equal to 0. So we're going to have the torque of the Achilles tendon, the torque of the reaction force, the torque of the normal force. Those are going to be equal to 0. Because I have my pivot point at the ankle where I have my reaction force, this is going to be 0. Okay. The Achilles tendon is rotating clockwise. So this is going to be negative. The normal force is rotating the object, rotating my toe along the ankle and anti-clockwise. So this is going to be positive torque. So I'm going to have minus the force of the Achilles tendon times 0.04. That's the moment of arm. Plus the normal force, which is going to be 65 times 9.8 times 0.12 meters. And this is going to be 0. And here I'm just going to do a little bit of algebra. And again, this is moment law. So, Kelly, the torque of the weight of the person, that's the normal force. So instead of looking at the weight, we're looking at the push of the weight on the person. So from here, you can see that 0.12 over 0.04, that's going to be a factor of 3. So this is 3 times the weight. So this is going to be 1,911 newtons, which is 3 times the weight. So your Achilles tendon is supporting 3 times the weight that you have. Now, I'm going to look at, does this make sense? Yeah? Okay, so now what I'm going to look is at the reaction force. Okay, and I'm going to do it over here. I'm going to look at my free body diagram. And I have normal force going up. I have the force of the Achilles tendon. And I have my reaction force. And again, I don't know which direction is the reaction force, but I'm going to assume that is positive. So it's going to look a little bit, how you call it, clutter, but I'm going to say that this is my reaction force. Now, notice that the normal force and the Achilles tendon force, none of them have components in X. They only have Y components. So because everything has to be 0, if we don't have components in X, that means that the force, the reaction force doesn't have any component of in X. So the reaction force only going to have a component in Y. So in the Y direction, I'm going to have the normal force plus the force of the Achilles tendon plus the reaction force. That's going to be equal to 0. Oh, sorry. The normal force is going to be 65 times 9.8. Sorry. I'm going to do it over here. I'm running out of space. So the normal force is 637 newtons. The Achilles tendon force is 1,911 newtons, plus the reaction force equals 0. The reaction force is going to be negative, and this is going to be negative 2,548 newtons. That's going to be the reaction force on the ankle.
Why is it negative?
So if you look at these two forces, and the forces are going up, you need to cancel those forces somehow. So that's gonna be the weight on the ankle and it has to go down. Otherwise, if all the forces were positive, you will be jumping. Okay, makes sense? Wednesday, we're gonna do a couple more problems involving looking at the shape of a squat, of someone doing a squat. And I think that will help you guys understand a little more the moment of arm. You can see them very clear there, and you can see how hard or difficult it is to measure the angles. So we'll do that on Wednesday. If you have questions for the homework, bring them in, and we'll do it here in the class. And we'll just make sure to do a quick review and make sure that you have everything you need for your exam. Okay? Any questions? No? Kaylee, did I answer your questions about the talk?
Yep, thank you.
Okay. That will be it. See you guys Wednesday. And have a good day.
Yeah.